Okay, so let's talk about transformations of power functions. So we talked about transformations a while ago. And we did it with quadratics. We're just going to do the exact same concept with power functions. So before we do that, let's run through again how to interpret these transformations. So let's say I have y equals x squared, right? So again, just what we talked about with quadratics. So y equals x squared. So if I have something like this where f of x equals x squared plus 3, right? This is just transforming y by adding 3. So really x squared plus 3 is y plus 3 because y is x squared, right? So x squared, x squared. So when I say, is this affecting the inside or the outside? That's what I mean. I mean that x squared is y, and then I'm just adding 3 to the outside of this function, right? This y, and then that's how it'll transform. So what's going to happen? You're going to add 3 to all the y values. So adds 3 to all the y values. That's what's going on. Well, what if I had something like this? You can see it's x squared minus 1. So again, in my language, I say that the minus 1 is on the outside of this function, this parent function. So since the x squared is y, it's really y minus 1. So this, in effect, will subtract 1 from all the y values. Okay, so that's the transformation. How about something like this? Well, f of x equals x plus 3 squared. You can see that the y is x squared. So this plus 3 is not on the outside of the square. So this is not affecting y's directly. It's actually affecting the x's. So any x I plug in is going to be affected by this plus 3. Now, to compensate for that, and this is how the insides work, I need to compensate for this plus 3. So in order to compensate, I need to subtract 3 from all the x values. All right? Because I'm adding 3 to all the x values, in order to get it back to where it was, right? The transformation would be subtract 3 from all the x values. All right? Okay. Next one, same thing. This is x minus 1 all under the square. So, right, in my lingo, I say on the inside. So it's not affecting the y directly. It's affecting the x. So when I plug in x's, I'm going to subtract 1 from all of those. So to compensate, I need to add 1 to all the x's. All right, so that's how this transformation works. And how about this? Where I have 3 times x squared. Same thing. X squared is y. I'm multiplying that by 3, so I'm really multiplying all the y's by 3. So again, in my language, I say that 3 is on the outside of the x squared. And since it's on the outside of the x squared, it affects y. And how does it affect y? It multiplies all y values by 3. Okay, the next one, let's say I have a 1/2 times x squared. Again, the 1/2 is on the outside, right, in my lingo. The x squared is the y, so it's really a direct effect on y. It's going to have a half times y, so this multiplies all the y values by a half. All right, our next one. Now I have a 3 times x. It's underneath the square. So in my language, right, I'm saying that this 3 is on the inside of the function, the parent function. So it doesn't affect the y's directly. It's not on the outside. So now it's 3 times the x's. Now I have to compensate. So I'm going to multiply everything by 3. So to compensate, I need to divide all the x values by 3. That's how I compensate. That's the transformation. Okay, same thing. X divided by 2. It's on the inside of the square, so it doesn't affect the y's directly. It affects the x before I plug it into to square it for the y. And I'm dividing all of this by 2. So in order to compensate, because it's on the inside, I'm going to multiply all the x's by 2. All right, our last one. Here I have f of x equals negative x squared. Again, x squared is y, so this is negative times x squared, negative times y. Again, it's on the outside of the x squared. Again, that's my language. So this is going to take all the y's and multiply by a negative, which means it's going to change the sign of all the y values. All right, and then our last one, a negative times x inside the square. So I'm not affecting the y's directly. I'm affecting the x's before I do the substitution. And so now what's this negative going to do? It's going to change the sign of all the x values. Has to. so let's try this. So I want to state how, oops, not each, but I'm only going to give you one equation, how the equation that I give you is a transformation of this power function, right? And I want it, again, in the classwork, I want you to be specific. Tell me how the x's and y's are being affected, just like I did, 2 seconds ago. After you state the transformations, I want you to state the end behavior, and then we're going to sketch the function. All right, so here's the deal. I have y equals axp, a power function. So now this is my transformation. So what's the original power function? It's x to the fifth. That's the original power function. So what is happening to this x to the fifth? Well, I have two things going on. All right, so x to the fifth is the y. All right, I know it gets confusing because I'm using y here, but x to the fifth is the parent function. So this minus 2 is on the outside of this parent function, and this plus 1 is on the inside. So this plus 1 will affect the x's. So when I add 1 to all the x's to compensate, I'll need to subtract 1. So that plus 1, again, underneath this fifth power, so it's inside the parent function, I'll need to subtract 1 from all the x's. This minus 2 is outside, so once I do all this work, I'll get my y value, and then I'll subtract 2 from all of those. So that negative 2, or subtract 2, subtracts 2 from all the y values. All right. Okay, let's talk about end behavior. Well, again, this is a fifth power. It's an odd power. Well, we know that odd powers make negatives negative and positives positive. So if that's the case, as I go to the left, it's going to end at negative infinity. So as x goes to the left, so as x goes to negative infinity, y will go to negative infinity. And why is that? Because odds make negatives negative. So as x goes to negative infinity, to the fifth power, we'll also make the y's go to negative. And then same logic, as x goes to the right, so as x goes to positive infinity, right, odd powers make positives positive, so the y has to go to positive infinity. So as I go to the left, the y's will go down. As I go to the right, the y's will go up. They have to. All right, so if we use all that, let's throw up our graph. I'm going to start with the transformations. So if you remember your parent function, the fifth, right, it's this squiggle, and then it kind of changes. Well, it was called changing concavity, but it kind of changes. The middle of the squiggle is right at the origin. So that's the point that I'm going to subtract 1 from the x and 2 from the y. I'm sorry, I'm going to add 1 to the x and subtract 2 from the y. So that's my point. Okay, so that's the middle of my odd-powered squiggle. Well, now I'll just draw my squiggle. And then you'll notice, and we could do a few graphs, but as the power gets larger, this actually gets flatter. That's the only difference. But you still have the same shape for all odd powers. But as the power of the odd gets larger and larger, it really gets flatter and flatter around this point. That's the only difference. All right, that's it.